It's an imaginary number. Because what is the square root?
Call it I.
Yeah, because if you plug it into a calculator, square root of -1, you get an error. Yeah, domain error, exactly. So it means that it doesn't exist. So technically in maths we call it an imaginary number because it doesn't exist.
That's an imaginary I. I would buy that shirt and rock it.
Yeah, there's a lot of them out there. So from the t-shirt image here, as you said, what do you think the mathematical symbols are saying? So it's that being square root of -1. I'm not sure what it is. This thing, see that thing is the one from here?
That means all.
Yep. So that one is I for imaginary. I8. So technically you can say all that, but mathematically I think, did someone say, Katie, did you say the something of? Yeah, so technically it's the sum of. Yeah. I8 the sum of pi. So that's what that bloody symbol up here stands for. It's sigma. So that's what the t-shirt says. You see it around. Sometimes we used to have a thing of it here. Is it gone? Some of them got a bit tacky, so we ripped them off. We'll have to put new ones up. So as I said, this lesson's more about, the math is easy, but it's more about language, understanding the language of the symbols and notation that might be coming up in the next few lessons. So therefore, what do you think the letter blah blah means in mathematics in general? Actually, you said it already. The sum of, yeah. I forgot that. I was going to ask that again later. The sum of. So the sum of something. And it's the letter sigma, by the way. So sigma, you know how there's alpha, beta, gamma, delta. Anyone want to have a guess which alphabet they think it comes from? Greek, yeah. Kind of looks like that Greek writing too, doesn't it? Alpha, beta, gamma, delta, that kind of thing. Sigma. Which letter in the alphabet do you think it represents? And a clue is in the name.
E.
Oh, it does. Actually, yeah, that's understandable, actually. S, yeah. It stands for S. I didn't think of that, but yeah, it does. It looks like E. Which would be the more obvious one. S. Which letter does from the alphabet do you think it represents? So the hint was sigma is its name. So it stands for S. Cool. So in the formula booklet section for this unit, this letter, sigma, I don't know why I wanted you to write it. I think just to get into the habit of writing it. That's a pretty dodgy version of it. Represents formula to do with the something of the terms of the sequence. What am I going on about? What? Because it's not even here, is it? So I wrote this a few days ago, and what was I thinking? Section for this unit. This letter, sigma, represents formula to do with the sum. So by sigma, I meant S. I meant that one, sorry. I know what I was thinking. So this letter S represents formula to do with the sum of the terms of the sequence. So the S that I'm talking about are here. So here's one with S. Here's another one with S. And here's another one with S. So just notice that they're connected to the word sum. 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 So sigma is a Greek letter for sum. In the formula booklet, sometimes they'll say S. So that's a hint that's kind of connected to the sum. I put this here just so you're aware that that's what the front of your formula booklet looks like, in case you're ever looking for it in your binder. So there's 3 sum formulas that we haven't learnt about yet. As I said, we've learnt about this one in lesson 1, we've learnt about this one in lesson 2. So this is an intro because we're about to get up to some lessons about these sum formulas. The sum of all the terms in an arithmetic sequence and the sum of all the terms in a geometric sequence and an infinite geometric sequence. Let's get up to the bit. So a classic question to do with sigma notation. You could be asked to evaluate the following. So if you see the word evaluate, your answer is always going to be starting with M. Evaluate, your answer is not going to be a formula or an equation or anything. It's just going to be a number.
Your answer always starts with M. What did you say the answer was?
Oh, it's that number. N for number, yeah, that's it. Just giving you a clue. So you could evaluate the following. You could be asked to evaluate the following. Evaluate means the answer will be a number. In case you ever forget, just so that you kind of are aware of that, means the answer will be a number, like not an expression or anything like that. Normally, it'll be a number. So evaluate the following means your answer is going to be a number. So that could be a clue. If ever you saw a question like this, evaluate the following, and you looked and went, what are they asking? The word evaluate might give you a clue. They want you to calculate a number. And that might kind of generate some memories of this topic. So you've got your sigma. So the sigma is the big symbol there. So it means the sum of all the numbers that satisfy this formula. So that's the formula. The formula would be provided. So the formula could be a totally different formula. It could be n squared. It could be 2n plus 5. It could be n cubed. It could be n over 7. So the formula for the terms will change from question to question. So just so you're aware, that formula is just an example of a formula. Will change from question to question. Just occurred to me that you might think that it's always that formula, but it's not. So when you see sigma notation, you do always see the big sigma, the sum sign. You'll be given some kind of formula. You'll always be told down the bottom, you'll always be told what the first value of n is going to be. Technically they call that the index of summation, not a big deal, but technically this is important. That's the first value of n, so they mean the sum of all the numbers that satisfy that rule, starting from when n is 1 up to the last value of n is 6. So first of all, in this sequence, how many terms do you think there are based on that information? From the first to the 6th term? 6, yeah. So it's meaning the first 6 numbers of this sequence, and they want you to add them all together. That's basically what they want you to do. They want you to sub in n is 1, that's your first term, n is 2 to get your second term, n is 3 to get your third term, all the way up to n is 6 to get your 6th term. Once you've got those 6 numbers, they want you to add them together. So that's demystifying what this is asking. So that's totally mainly what this whole topic, lesson 3, is about. It's about just understanding. If in an exam they just said, evaluate this, you could look at that and understand what they were asking. So we'll do a few examples like that. So as we said, it's just all about mathematics and language that we invent for mathematics. So what would be the first term in this sequence out of interest?
4.
Yeah, 4. 4 times 1. Second term will be 8. Third term, 12, yeah, and so on. So what kind of sequence is it? Is it geometric or arithmetic? Good guess? Okay. Yeah, it seems like it because you're multiplying with a formula. But yeah, when you write it out, we have an answer this one eventually. We're not bothered writing it out yet. 4, 8, 12, 16, and so on, 20, 24, that's the first 6 terms. If you see it all written out like that, it's technically an arithmetic sequence because you're adding 4 each time. That's just a flashback more to lesson 1. So a quick flashback to lesson 1. Okay, so write as a sentence in words what you think the above question is asking. So you could write it in your own words. Offer. So it's asking you to, let's say, work out or evaluate. Work out the sum of the first 6 terms for a sequence which follows the rule 4n. It's more like, how could you say that in a way that kind of makes sense to you? So if you want to rewrite it in your own words, in a way that makes more sense to you, that's okay. So they'll tend not to, in an exam, ask you to write it as a sentence in words. This is more just for your own personal reference. So work out the sum of the first 6 terms, or you can say from term in the first to the 6th term, add them all together for a sequence which follows the rule 4n. And as I said, the rule's going to change from question to question. They'll probably also not all, they might want you to say n is 2 and the last term is 6, the sixth term. So that means work out these second, third, fourth, fifth, sixth, seventh, eighth and add them together. So those numbers at the top and the bottom of the sigma sign can change too. Then it says now work out the answer to the question. So basically it's going to be things like that. So we'll do a little example just pointing out how we got the first and second term maybe. So the first term will be 4 times 1 equals 4. Just a few little examples of finding the term. Second term, 4 times 2 equals 8. I'll do the third term and that'll be it. 4 times 3 equals 12. Just in case in a few weeks' time you look back on it and go, how did we get that sequence? It's all to do with the fact the rule is for n. So the sequence is 4 plus 8 plus 12. So basically that, because it's a sum of, we need to add them all together. 16 plus 24. And we're going to work out that answer. You can do it by hand if you want, you can do it with a calculator. Just do it moments to do that. And then what the answer is.
84.
Probably. It says, can we have one more confirmation of that? Yeah, okay. 84, we'll go with it. So the answer was 84. So that weird notation at the top was just asking you to work out this number, 84. So that's just reminding you, evaluate means the answer is going to be a number, generally at the end. So just some more practice of that. So recall back to our TOK intro lesson. What did Gauss's teacher, Buttner, ask his students to do? Yeah, that's right, yeah. Add the numbers from 1 to 100. So it's kind of like asked to work out the sum, isn't it? From 1 to 100. Now write the teacher's question. How would he have communicated that if he had to write it on the board in sigma notation? So the first thing I'll do is that new sigma sign. So I told you look in sigma. But yeah, generally they'll understand what you mean. Interestingly enough, what would be the formula? The numbers from 1 to 100. It's a really simple formula.
N.
Yeah, it's just n, isn't it? So that would be your formula, just n. Because from 1 to 100, first term, second term is 2, third term is 3, fourth term is 4. So the n value corresponds to the term, doesn't it? So it helps you can write that. You just find out what we're talking about. Plus 98, plus 99, plus 100. That helps. You can see that n. That's the first term, second term, third term, 98th term, 99th term, 100th term. So the formula is just n. What value of n do they want us to, first of all, add the first term, or do they want us to start from the 6th term or the 8th term? The first term, yep. So it's pretty obvious. So if you're not sure, have a look at how we did it. N equals 1. So it might be tempting to just write 1. But
So if they wanted us to start the 6th term, it would be N equals 6.
yeah, exactly, yeah. So if they wanted us to start adding from the 6th term or the 3rd term instead, then n would be 3. And how many terms in total do they want us to add together? 100, yep. So if we're starting from the first term, the last term will be the 100th term. So it's a bit of a confusing one because the n happens to be exactly the same as the position. It's not really. Yeah, so there you go. So that's how Buttner, the rugby teacher, would have communicated his little challenge to the students in sigma notation. He might have also had a little instruction. What instruction would he have had? The word from the top of the previous page starting with E. Yeah. evaluate. Evaluate the following. You can just say evaluate. And technically here. Evaluate that. If he was a man of few words, he would have written it on the board like that to make it even more difficult. So we're going to do a few more examples. As you can see examples of where the formula changes, the formula varies.
You don't have that. Oh yeah, we don't have that.
Oh, don't you?
It's just blank. Yeah.
That's weird. Is it on the next page?
No.
Oh no.
Oh, we can just.
You've got that though, don't you?
Yeah.
Oh, do you have space to write it?
Yeah.
It's almost like a whole extra page.
Then we have the bottom ones.
You have the bottom ones? Where are they?
We just have this.
Oh, that's so fun. Okay. Oh yeah, might have a flashback to thinking that happened, yeah. And then because it was so many days ago, I forgot. I must have printed it before I added that in there. Sorry. Yeah, so you've got the space A and B though. So in A and B, they want you to write that. So give you a bit of time to write that first. The big symbols, yeah. Can be pretty simple, like they would understand if you did it a dodgy version like that. That looks nice though. I don't care if you've got the little drop. Out of interest, the first rule, is that, would you say that's a linear rule, or a quadratic, or a cubic, or geometric?
Linear.
It's linear, yeah. So that's an arithmetic sequence it turns out to be, just out of interest. What kind of sequence could this one be?
Cube.
Maybe? But even just like what kind of formula is that? Is it linear?
Quadratic.
So yeah, quadratic, yeah. So just out of interest, just while you're writing, that's a quadratic sequence that way. So an arithmetic, linear, and quadratic. So we would need to evaluate the first 6 terms. So the first thing to do is write out the first 6 terms. So the terms are, you can try working out for it if you want. You're basically generating something for you to look back on and understand how you got the answer. So first it then starts with 1, the first term must be 2, then 2, 3, so on. Oh. In which case I'm going to write 2 plus, just to remind myself what that is. It's a bit boring because this is going from the first to the 6th term again. But the next one at least is a bit different. So you just want to check you've got the 6 terms out and you just add them together. Oh, what do we get? 42. Cool. If anyone disagrees, let us know. 42. So in a way, technically, it's not the terms are. So I'm going to get rid of that. Doesn't matter if you wrote that. So I end up summing them instead. And then the next one, notice they want us to start with the 4th term. So you'd start by subbing in 4 into here. So as a memory, let's generate a memory for ourselves or a little reference for ourselves, just a point so we can look back and see how we got the first and the 2nd term maybe. So we've got to use bed mass. What's 4 brackets for? Put bracket squared.
I mean 64.
Yeah, it's 64, yeah. You got to square the, well, you would get the same answer anyway, I think, almost. Oh no, you wouldn't. So bed mass, you've got to square the 4 first and then times by 4. It would be 64. Then 4 times 5 squared. 100, yeah. So we could start to write it out if you want. 64 plus 100. They only want us to go from the 4th, 5th, 6th, and 7th. So what would be our next term? 144, sounds good. 4 times 36. And then the last one, 7. Yeah, 49 times 4 basically, because 7 squared times 4. 196, is that right? And then we just add them all together. Notice they're giving you nice ones where you don't have like 15 numbers to add together. in this topic. Thank you. And then same thing, they want you to write this in that form. So go back to being a footnote. We kind of, in a way, probably the most challenging thing is we kind of need to work out what's that going to be. And I guess we'd assume that's a first, a second, a third, a fourth. That's a first, second, third, fourth, fifth. And then we'd have to work out which term number is that. Yeah, that's good. How did you see that?
How did I see that?
Yeah.
Because the top right here is offline 1.
Yeah, so that must be the 12th term. So it's going from the first up to the 12th. So first thing we have to do is we write that big sigma sign, however you like to write it. So it's n equals 1. And it's just going up to the 4th, so 4. Okay, so interesting kind of formula here. So our formula is going to have, for example, actually technically it's not n, is it? It's b. Yeah, thank you. Didn't notice that. B equals 1. So our formula's got b in it instead. So it helps write out your n. 1, 2, 3, 4. You see a connection between the n and the coefficient at the front?
It's something b plus 1. The experiment will be b plus 1. Or b subtracted.
Yeah. Yep. Oh, and yeah, the coefficient, this number here.
But I mean the experiment.
Oh, the exponent? Because the exponents are...
Would be, should just be.
Yeah, the exponents would be just b, correct? And the coefficient, the little numbers out the front. Yeah.
B plus 1.
Yeah, it is, isn't it? That's a big get. So b plus 1. B plus 1. But then don't forget you're multiplying by b. And it's all to the power of b. Yep. So you could write it simply like that. You could also try expanding it if you want. You could write b to the power of b plus 1, you know, exponents and that kind of thing, but that's a bit, factor that in.
B.
Oh yeah, that's a b. It does look like a 6 though. Try to make it look more like a b. So maybe say the coefficient, we can write a little code for ourselves, is the coefficient is b plus 1 and the exponent is just b. Hang on, I think I've done this a bit dodgy, haven't I? Do you think I should have kept it as n? No, it's fine, isn't it? Yeah, that works. It just is, this one's getting really confusing. So this one as well, as we said, we're adding together the first 12 terms, the dot, 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 and adding the ones in between. With my notation sign. And we're going to start with the first term. We call that n1. Well, involve n. N equals 1, 3, 4, and so on. And we're going up to the 12th term, as Kirsty noted. Notice that the n happens to be the numerator. So we're going up to the 12th term. So if we're using n, what's the connection between n and the numerator?
It's just the same.
It's just n, yep. So it's a fraction, the formula, where n is the numerator. And can we see a connection between n and the denominator? Is it n plus 2?
Yes. And then
Yeah,
one
we can test it for all of them. Yes, we can.
N times 2 plus 1.
Yeah,
Yeah.
it's basically n times, if you double the n, and you add 1.
So 2n
You
plus
get the denominator. Yeah, so 2n plus 1. So you might want to write it a bit bigger actually, to give myself some more space. N over 2n plus 1. Yeah, so that will do. This one I'm still dodgy on my answer to that, so I'll get back to you on my answer to A. I'm wondering, should I just have left n? Should I have kept that as n, the exponent is n, and that is n plus 1? That maybe would have been better. I feel a bit weird about my answer. So get back to you, and I'm wondering whether I should have just called that n and that n plus 1 and left that as b. So I'll get back to you. Okay, so I think that's the main thing. So we're doing it. So you can see it's just communicating. A little bit of practice. So you would need to be able to find the rule as well. So a bit of practice of sort of seeing the rule. Sometimes writing the n, as I said, sometimes writing the n above everything. Sometimes writing the n's out like 1, 2, 3, 4, 1, 2, 3, 4 could be helpful. It helps you to sort of see what the rule might be. So this is just a little gag at the end. So more about Gauss from our TOK lesson. So we taught, you noticed that in our TOK lesson, some of you saw a whole heap of Chuck Norris jokes on the internet. So similarly, what's weird, after that lesson, I didn't realize at the time, but after that lesson I was looking up Chuck Norris math jokes, and I found out there's a whole thing to do with Gauss as well. So similar ones where it's about this mathematician Gauss, because he ended up, after like not only just being a child prodigy, he ended up being kind of quite prolific in mathematics and a bit of science as well. So what do they have in common? They've both been the subject of fact culture. They call it like Chuck Norris facts, Gauss facts, and that kind of thing on the internet. And sometimes in similar ways. So sometimes they have similar kind of dull jokes made about them. Just as there are plenty of websites out there with Chuck Norris facts. So for example, the mathematical ones, best mathematical ones are probably this. We counted to infinity twice. The square root of -1 is not imaginary, it's just hiding from Chuck Norris. So remember like I. So remember square root of 1. Square root of -1, sorry, equals I for imaginary. Chuck Norris knows the last digit of pi. Why is that a joke? Yeah, exactly. There is no last digit of pi. It's an irrational number. Oh, do you?
She was better math. Yeah, Mr. Moore is boring.
Hopefully that doesn't help. Okay, the square root of 2 is a rational number for Chuck Norris. So in reality, what kind of number is that? Is it? It's an
It's 1 point something.
It's a rational number or irrational?
Yeah, exactly. You're right. That's a joke. So the square root of 2 is a rational number. So it is not being irrational because Chuck Norris is so intimidating it becomes rational for him. The shortest distance between 2 points is Chuck Norris. So there are similar ones to do with Gauss, and I've tried to put an image kind of related to it. And oddly enough, a lot of the jokes have to do with the SL course, and maybe a little bit of what you've learned in CIE as well. So you learn a thing in this course called the normal distribution. And do you remember me telling you about the way kind of grades are worked out, like the 1 to 7 kind of thing? Like they kind of, it's been assumed that a lot of things in nature, including human intelligence, follows this strange distribution called a normal distribution. So if you kind of like worked out the heights of people around the world, the majority of people are kind of average height, so the average goes through the middle. And then a few are kind of like a little bit shorter, a lot are a little bit taller as well. And there's only a tiny amount of people that are mega tall.
Yeah, that helped last night. I just laughed, but it's like so crazy.
Yep, a small amount of people are really short. So this represents kind of like the population of people.
His leg.
His calf.
Is that?
I was reading that.
Up to his belly button.
For a woman, that's something that's honestly like 160 centimeters. I'm like 172, so I'd say like
172 centimeters?
Yeah, 171, sorry. So I think the average would be about here. I'm guessing, because I remember it was February. bit shorter, surprisingly. And so same thing with you look at the length of lizards around the world of a particular species. Strangely enough, they'll follow. The bigger the population that you sample, the more it seems to follow this weird mathematical curve. And it's assumed the same with like human ability. So that's why universities and examining boards like the IBs, they could generally use the general idea that like a majority of students in the IB are going to get like for a 4, a 5, a 3, 4, or a 5. Majority will get 3, 4, and 5. There'll only be a small amount that'll get 6s, and an even smaller amount of people will get 7s. Only a tiny amount will get 1s. A slightly bigger amount will get 2s, and so on. So majority are going to get like something in the middle, like 4 or something like that. So that's just pointing out that you kind of are generally competing against students around the world. In the IB, apparently they do something a bit more complicated. They do this double curve kind of thing. I don't know exactly what it is, but that's the general philosophy of this whole, the way they kind of distribute who gets the 7s, how many people are going to get 5s this year, how many people are going to get 6s. And this guy Gauss invented that mathematics. So he came up with the normal distribution. So another name for it is the Gaussian distribution. So he's saying like, a certain percent, like 60% generally are within this spot here. Most around the average, most people are kind of here, close to average. Only a few people, tiny population, that's why there's a small area underneath each one. That's a topic you learn in this course. So normal distribution is actually a topic. So the joke, by the way, is Gauss didn't discover the normal distribution, instead nature conformed to his will. Gauss, he didn't discover the normal distribution. Instead, nature just made itself follow that mathematics and conform to his will. Because generally, like, he generally came up with this after looking at loads of data, like loads of measurements of things in nature and things in society and stuff like that. So it came from lots and lots of data generated this. So they're joking that the world instead, he came up with it and the world conformed to it instead. So that relates to your topic, the normal distribution. I like that one. Because you're so intimidating that the whole of nature conformed and started to follow that pattern. Parallel lines meet where Gauss tells them to. So what's the joke about that? Yeah, exactly. Parallel lines. Gauss can write irrational as the ratio of two integers. So do you remember rational numbers? This is a bit maybe from CIE, and it's also implicit in your course SL as well. Rational numbers in theory can always be written as a fraction, where A and B are integers.
Yeah.
Like whole numbers can be positive or negative. A and B are integers. So the number, for example, 2.5, how could that be written as a fraction with the whole number on the top and bottom? 2.5 is the same as a fraction? 5 all combined. All of you have said the right number at some point. 5 over 2. Yeah, 2.5 could be written as 5 over 2. Yeah, something like negative 0.3 recurring could be written as negative 1/3. Whereas irrational numbers, by definition, can't be done like this. It's impossible to write pi as a fraction with a whole number here and a whole number there. And same thing, square root of 2. It's impossible to write the square root of 2 as a fraction with a whole number here and a whole number there. So that's a joke. Gauss can write irrationals as a ratio of two integers, two whole numbers. Gauss doesn't look for roots of equations, they come to him. So by roots of equations, they mean like the answer to when you do the quadratic formula. When you are factorizing and solving for a quadratic, you're finding technically the x-intercepts on the graph, which another name for that is the roots of the equations. So roots of equations are the x-intercepts. So the roots of equations are the x-intercepts. It's basically what would you get if you solved a quadratic. So e.g. you solve x squared plus 5x plus 6 equals 0. So if you solve that, you would get x equals something, x equals something. Anyone want to have
Yes.
If you factorize that, first of all.
X equals 1.
Those are the things, you know.
Yeah, I just want to.
X-
Yeah, I just kind of want to do it now. Yeah, good. X plus 2, x plus 3. There's 2 times 3 and 2 plus 3. Good. X plus 2, x plus 3. So what are our two roots?
Negative.
Yeah, that's right. So they're our two roots of the equation. So the joke was Gauss doesn't look for roots of equations, they come to him. So he doesn't do the solving. They just come to him. Yeah, so you'll be doing heaps of like finding x-intercepts. There are no theorems, just a list of propositions Gauss allows to be true. So like saying there's no kind of mathematical formulas, just a list of things he just made up. Oh no, a list of things he said it's okay to be true. When Gauss integrates, integral calculus is the topic that you'll be doing. Integral calculus. So you might have done a bit of differential calculus. So remember, differential calculus is when you're kind of like asked to find if y equals 4x cubed, what is dy dx or y dash? So can anyone remember differential calculus? If you were asked to...
I've never done calculus
Yeah.
before.
4 times 3 is 12 x minus 12x.
Yeah, good. Very good. So that's differential calculus. Integral calculus is when you're doing the reverse step. What if you had to go from here to that? So that little sign means integrate, means do the reverse. So here's the answer to the derivative. Turn it back into the original. And the reason why that's a constant, that's just a number. Because for all we know, remember if you had plus 4 here, for example, 4x cubed plus 7, for example, if you differentiated just a regular number, what does it happen to it? Does it appear here at all? No. So it's gone. So when you do the reverse step, there's always been a mysterious constant. So when we have to differentiate, we generally write plus c at the end because we don't know what that mysterious constant was. If we only know that was the derivative, and we were asked to go back and get to here, we could say, yes, we know that this came from here, 12x squared, when you integrate it was 4x cubed. We don't know what the constant term was, so we just write plus c. So when Gauss integrates, he doesn't need to add a constant. So he doesn't need to do that. He just goes to there. We're almost there.
So then it was the first one, your favorite one?
Yeah, for sure. Yeah, they're getting a bit less impressive now.
Can you send me this recording?
Oh yeah, I don't really need to record this part. Primes that aren't Gaussian primes get teased. So there's things called Gaussian primes. If you're interested, you can read that little thing. If you can read the print. If Gauss had to walk 100 meters, and then half the remaining distance, and then half the distance again, and so on, he'd get there. So if he had to walk 100 meters, plus half the remaining distance, and half the remaining distance, so like 100 meters, and then whatever's left, he would walk half that distance, and then half that distance again, and then half that distance again. In theory, he would never get there, would he? Whereas he does.
Like, that was
Yeah, so imagine his destination is here. Here's the house. So he's walked 100 meters. Then half the remaining distance. And then half the remaining distance. And then half the remaining distance. And then half the remaining distance.
got there.
half the remainder. So in theory, he wouldn't get there. That's what that's
Because I'm a
It was fun going to
What are you doing?